Welcome to the Nanoseminar conference series in chemistry and materials of ICN2. We are located in Barcelona, Spain. And today we have the presence of Professor Udo Bach from the Department of Chemical and Biological Engineering from Monash University in Australia. But as we do with this Nanoseminar series, before our keynote speaker, we invite postdoctoral students or invited students to give us a 10 minutes presentation, and today is different from other occasions because we have two mini talks. And the first one is, the first introductory talk is labeled A Detailed Study of an Alternative Materials for Earth Abundant and Recyclable Solar Cells, and will be given by Chiara Spadaro she's a postdoctoral researcher here at ICN2 in the group of the Advanced Electron Nanoscopy group at the ICN2. And our second mini talk, introductory talk, will be an invited student from Professor Henry's Knight laboratory, and he's going to talk about the stability in PIN, low temperature carbon cells. After them, we will have our keynote speaker. We'll introduce you to our keynote speaker, and we will have all the question and answer at the end. So I will invite all the people joining us from online to use the chat to make their questions, and we will read it at the end. So let me introduce to Chiara and enjoy.
Well, ideally, we would like to improve the solar cell from one side in terms of the efficiency, and for this reason, novel materials are being proposed, such as perovskites, which will be introduced later on by Professor Bach. And on the other side, research is currently developing in order to improve the architecture of the devices, making them more thin, because for silicon solar panel, we are in the micrometer range, and currently what we would like to have like comparable or a good efficiency absorption with the nanometer thin solar panel in order to have more flexible and transparent, being able to implement them in our window in our houses. The material we investigated for this purpose is the zinc phosphide, which possesses a tetragonal unit cell here depicted. And as we can see, the C-axis is much bigger than the other two axes available. This type of material has been proposed for solar cell application almost 40 years ago, finding a very low efficiency of around 6%. And the main reason for this is the challenge of making this material growing on the currently available substrate, because with such a big unique cell, it's difficult to find a material where it can easily adapt. But in these 40 years, the material grow methodology have been improved. And a couple of years ago, our collaborator at EPFL tried to obtain this type of material, zinc phosphide, on top of indium phosphide. They started growing it with vapor liquid solid growth, therefore obtaining this vertical nanowire. And depending on the flux ratio between the zinc and the phosphorus material, and the temperature of the substrate, they could tune the morphology from vertical, straight tilted nanowire, zigzag, and crawling. Observing that the best one, the most promising for photovoltaic application, is the vertical nanowire. But for this type of morphology, basically, in order to create a proper device, we would need to remove the nanowire from the substrate, many of them, in order to interconnect them in another substrate, making this process pretty expensive and with a low reproducibility. Recently, another synthesis route has been introduced, which is the selected area epitaxy or growth, in order to obtain the so-called horizontal nanowire. These methodologies here sketched. Basically, we start from the substrate of interest, and on top of it, we deposit the oxide mask. Then, thanks to lithography, we can create some aperture on the mask. And this aperture can be either circular, obtaining the so-called nanopyramid depicted in here, or it can be with specific orientations along the substrate, obtaining the horizontal nanowire here depicted. And this is the case that we investigated recently. And in particular, as we can see here, depending on the aperture orientation on the substrate, we can obtain a different material orientation combination. And once we select the best one for photovoltaic application, we can easily create a solar cell device that with the same technique, therefore that it is easily scalable. In particular, the orientation we investigated, we selected two orientations. The first one where the 100 zinc phosphide is parallel to the 110, the indium phosphide. And the second one when the 110, the zinc phosphide is parallel to the 010 direction of the indium phosphide. As we can observe in both cases, from the image crystal quality point of view, from the power spectrum analysis, we can observe that the zinc phosphide is highly crystalline, growing epitaxially on top of the indium phosphide as it follows the same growth direction. The only difference is related with the interface between the nanowire and the substrate, because in this case, it is much more rough than in this other case where it's sharp. And this is related to the size of the aperture of the trenches at the mutual distance one to the other. In order to investigate possible plane dilatation and rotation within the nanowire after growing with this methodology, we perform a geometrical phase analysis by considering rotation and dilatation of the atomic planes that are parallel to the substrate surface and perpendicular to it, finding that in all the cases, the plane rotation is minimal, while regarding the plane dilatation, we can observe that in all the cases, the zinc phosphide planes, which are depicted here, are compressed with respect to the indium phosphide, indicating that the material is able to adapt. Thanks to this low size of growth, the material is able to adapt on the substrate, preventing the formation of mismatch dislocation, which would create problems for the crystal quality and therefore the application. Looking into more detail the structure of the nanowire itself all along the length, we could observe both from STEM HADF image contrast and power spectra analysis that the material presents secondary domain, here depicted in orange, that are related to the zinc phosphide growing in a rotated direction with respect to the main domain, which is in violet. And with further study, we could evaluate that this type of domain appear at the early stage of growth. When the material starts to fill the aperture trenches, many seeds are forming, and when these seeds possess the 101 facets, basically from here, the material possesses a different growth direction, which is the 110 instead of the 001, making it slightly rotated. Performing a detailed analysis on the entire length of the nanowire, we could observe that this secondary domain are not una tantum in the structure of the nanowire, but they are highly present in the length. In order to understand the formation of this type of domain, we created this 3D atomic model where we have the indium phosphide 001 substrate, where we deposit on top the mask, and thanks to lithography, we create this type of aperture. Then that is where the material starts to grow, depositing. At the early stage, we already observed the formation of a cluster of these seeds that possess specific surface termination, in particular the 101, where on top the material continue growing, but with a different orientation. We can see that the zone axis is the 111, while in the other cases the 100. It's important to notice that as soon as this type of domain appear, the rotation is kept until the end of the nanowire. Therefore, the structure doesn't go back to the original orientation, demonstrating that from a growth point of view, they are highly stable. But we wanted to investigate the effect of this type of domain into the photovoltaic application. Therefore, we were interested in studying the electronic properties of the material in presence of this domain. For this reason, in collaboration with Cardiff University, we could perform this density functional theory simulation, observing that the density of states of the material in presence of that domain is similar, is stable, as in the case of in case the domain are absent. In fact, there are no dangling bonds and no mid-gap states that could provide the recombination of the carriers. Concluding with selected area epitaxy, it's possible to grow high-quality zinc phosphide nanowires. And these nanowires present 120-degree rotated domains, depending on the facets of the seed at the early stage, that are due to growth kinetic variations. And this domain we demonstrated with DFT simulation that are stable from electronic point of view and from the structure point of view. I'm happy to mention that this work we performed is in the field of a European project, an EIC Pathfinder, which has been recently granted and is coordinated here in ICN2 in collaboration with the EPFL, University of Jena, Lund, TNO, and AMOLF. And the project will start in the next months, therefore stay tuned for the outcome. I would like to thank all the people that contributed to this work and all of you for your kind attention.
Hello, everyone, and thanks for tuning in and thanks for the opportunity to give a talk here. I'll talk today about stability in PIN low temperature carbon cells and perovskite solar cells. I just assumed that all presentations would be on perovskite. That's why I left it away. But yeah, it will be on PIN perovskite solar cells. Why am I using carbon at all? I am convinced that carbon electrode can solve 3 of the major obstacles for perovskite solar cells in their commercialization. One is the stability. That's one thing I'll focus today on. One is the low cost of the material itself. And the other one is like scalability, because you don't have a high vacuum process that you need for like other electrode materials. So carbon can hopefully deliver on all those 3. And I hope having convinced you, I dive into like one other detail, like we are here at the Institute of Nanoscience and Technology. And for those who haven't worked with carbon electrodes before, but with metal electrodes. So the metal electrode is usually several tens of nanometers in thickness. And here, just to give you an impression, this crystalline layer is the actual perovskite absorber. It's like half a micron thick. And the carbon electrode actually itself is like a rather thick film, so in the tens of micrometers, and it's extending out of the like this SEM cross section here, just to give you an idea like of the dimensions of it. And the long-term aim of my PhD project would be to have like a fully solution process stack, including the electrode, and have it done all in low temperature processes. That's why I go for planar PIN. Just to give you a brief impression on like what are maybe alternatives on that. One very common thing for perovskite solar cells with carbon electrode is this triple mesoporous. So this is the competitor to what I'm actually trying to do. It's very well established in the carbon electrode field and has shown to be able to deliver on the stability promise of carbon, and has like 3 mesoporous layers. One is like the Ti2 ETL, one is usually a mesoporous insulating layer, and in this configuration, the carbon is also mesoporous. But like these mesoporous layers are usually produced at like really high temperature, and that's why like most of these architectures don't have an HTL, because HTLs, most of them are temperature sensitive, as well as the perovskite is mostly temperature sensitive. That's why like in this case, like perovskite is infiltrated later into the cell. So but like a high temperature process usually has like is like less scalable in industry. You cannot do it on flexible substrates, one of the things that are really promising for like perovskite solar cells. So this is why I am going to use PIN architecture. And I started off with like using the exactly same configuration we use in our metal cells, and just simply very simple plate coat carbon on top of a ready stack. Oh, delayed. So you have the entire like stack finished, and then you apply the carbon as you do the exact same thing, but when you put it in a metal evaporator, you plate coat carbon on top. So that was the first idea of it. So we can build on all our knowledge and experience we have with our existing stack. So far the theory. When I first tried that, so just to give you a quick overview, this is my stack. So like the reference would be a gold with like minus 5.1 EV. And I will focus on the N side in PIN because that's the side that is in contact directly with the carbon that we're going to introduce. And carbon has a minus 5.0 EV work function. So it's like very similar to gold. So that's why like there was the initial thought that it would work. But when we do that, exactly that was like pictured here, we get like this kind of JV behavior. It's pretty ohmic, looks pretty ohmic, is pretty ohmic. It's not a solar cell at all. So this was what we initially get. So there is, for whatever reason, not working. So there were like a lot of thoughts initially. Is it the energy alignment? Is like BCP, like that what I use as a hole blocking layer, not making a good contact to the carbon? Is the carbon destroying the stack by plate coating that much that we get shunt issues? There was like some initial data looked like we got full shunts. So this is a method, this is DLIT, a measurement on like a 1 square centimeter of my carbon cells that was like not working, and shows like local heat dissipation, which would be like indicative of like shunts in these devices. So from that point, I started looking literature. There was not that much literature on like PIN carbon, and found something by Babu et al. From 2020. They introduced a chrome nano layer, just a few nanometers of chrome. I was not convinced that it would work. It did work. Like after a lot of optimization, we obtained like really good results with it, efficiency-wise. I was really happy. We got like, we beat like their efficiency in their paper by like more than 10%. But so I tested like to have something new, multiple like different metal nano layers in between, and looked at it. We had like promising performance, and all our devices was like this like few nanometers of evaporated metal that like seemed to protect our devices pretty well. And then the next step was like looking at our what I've promised in the beginning, the stability of this layer. And one quick thing, what we also did like for optimization was we changed from a hot plate curing to a heat gun curing, and that solved the initial problems we had. Initially we had like our carbon electrode detaching sometimes from the device when we're not handling it carefully, and had like an SEM image that looked like microcavities. But the heat gun curing instead changed that. And what was also really surprising to me is how short of a curing I needed with the heat gun, because usually with like in hot plate we like cured for like at least 10 minutes, and with the heat gun it was like looking like a 3-minute curing is like something that already delivers best results. And this is within one like study. We have like similar performance of the like really short cured devices to our, this is our like silver reference devices in that study. So we got like multiple devices for like in a 16, and like for long curing got like medians for like 8% stabilized efficiency to like 14 medians in efficiencies for like really short curing periods. And then we took the whole to like aging studies, and they had showed that the metal layer in combination with this kind of curing is like not what we wanted. So especially the bismuth layer that was one of the layers I tried, everything that contained bismuth was basically dying in like 1 day. So I won't recommend anyone to use bismuth and carbon in combination with perovskite. So we have, even in like a mild curing of like in nitrogen at like heat and dark, the bismuth devices were like dying, and they behaved really strangely. And like perovskite looked like very damaged and amorphorized. So there was like consistently, we have like no grain boundaries, but lots of holes in them. And it's not like beam damage, because like the same devices with like a chrome layer look like this. We see also holes, but we see a lot of grain boundaries in it. So it's like really strange behavior of the aging. And the chrome was still, but like in like the stability study, we see that like chrome carbon is like also not delivering the promise it had on stability. We don't know yet why. So even in like a longer, like this is also in nitrogen, it's like extended what I showed in the last slide, the chrome carbon is less stable than gold. So it was like for like PIN carbon, like first of like really disappointment that it's not beating gold in stability. And we first saw the chrome being the issue, but then it didn't look like the chrome as material as an issue, because when we compared like metal electrodes with a chrome layer and without a chrome layer, it looked like it made it even more stable. So at least no disadvantage out of it. And so we're like aiming for, after we achieve the stabilities, we have like higher stabilities than this firstly introduced, like maybe a lot of you know this paper is like the 1-year stability, which was on a triple mesoporous architecture, really impressive in 2017. So we want this kind of stabilities with our efficiencies, or maybe even a bit more efficiency than we got in a planar PIN carbon device. And the next things I'm planning to do is improve the curing and change the solvent system of both the carbon electrode setup and the N-type layer to maybe see what that does to stability. And one other thing is like plate coating is not the only way for like low temperature transfer of carbon electrodes onto ready stack. There's something called a press transfer, where you do the carbon electrode in one substrate and press it on your stack. So this is also something that can be tried instead of plate coating. This is actually out of a work last year out of Udo's group, who's going to talk after me. That's why I chose this example here, and found like a really interesting architecture. And ultimately, I also want to replace the chrome layer, which is the only working thing I have so far, because it's still an evaporated vacuum process, and I don't want a fully solution process device. So not yet a hero story, but a lot of ideas where I can go on. And thanks to my group, just to introduce them to you, it's a bit bigger than the group here. And yeah, thanks to a lot of people who enabled me to give this kind of talk and performance here, and to you all for your attention. Thank you very much. Questions or not? No. Okay.
So thank you very much to both of our speakers, very interesting talks. So now we are going to introduce our keynote speaker today. I just remind you, everybody, especially those online, that the questions are at the end, and please use the chat box. So our keynote speaker is Professor Udo Bach, and he's going to be talking about perovskite solar cells. Udo Bach is a full professor at Monash University and the Monash North leader of the Art Center of Excellence in Exciton Science. He received his PhD from the Swiss Federal Institute of Technology, PFL, in Switzerland, working with the Professor Michael Gratzel. He worked for 3 years in a technological startup company in Dublin, Ireland. He also spent 15 months as a postdoc in the group of Professor Paul Olivasatos in Berkeley in the United States, before he moved to Monash University in November 2005, where he started his own research group. So he's going to talk to us about lead halide perovskite solar cells. Thank you very much for being here. I'm very happy that you were able to make it from Australia with us. Thank you.
Very happy to be here. Big thank you for the people who made it possible for me to be here. And first and foremost, my hosts, Monica and Sonia. We always travel in order to learn. And I think over the last couple of days, what I definitely learned is that I got a really nice tutorial on how to be an excellent academic host. So you guys were really amazing so far. And I think I have to learn a lot from you. So thank you so much. And I also would like to put some thanks out there for the funding organization that is funding some of my study. Okay, so I will be here at the Institute until the 31st of June. And I even have an office here on the first floor. So I'm in office number 1103. And here is my email. So if ever you get inspired by anything I'm telling you today, just send me an email or just come knocking on my door. Cool. Okay, so I'm coming from Monash University. This is from a school book in Australia, the world map. And we're based up here. Let's see whether this is working. This is my first time. Yep, there we go. So Melbourne is here in the very south of Australia. And we're currently, I put the marker in, but no, it's here. And we're currently here in Barcelona. Melbourne is Australia's second largest city, so almost 5 million people by now. I think when I started, it was about 4. Now it's about 5. It's always been in the top 10 of the Economist's most livable cities in the world. We've been #1 for quite a few years, but now there's been a few people coming in, pushing us, but we're still in the top 10, so it shouldn't be too bad. And unfortunately, this is also something I'm not so proud of. We're the world's most locked down city for the COVID period. So that's 246 days. It felt a bit like that. Yeah. Cool. Okay, so Monash is the world's largest university. Over the last 2 years, there's a lot of international students. The 50,000 is still something that is a bit dated, so I'm not sure where we currently moved, but it's in that. I think we moved up to 60, 70,000, but now with COVID, this might be again actually a number that is quite accurate. And we're always somewhere in the top 100 in the Times Higher Education. This is a Nano Technology Institute here. I'm also part of an institute that is very similar to this one in Australia, and that is our Center of Excellence in Exciton Science. And I think one of the reasons also why I'm here is to get an understanding of what you do in your institute, what we do in our Exciton Science Institute, and see what the links are and how we can work together. So I'll talk a little bit about our Exciton Science Center. So the motto here is Next Generation Light Harvesting Systems for a Sustainable Energy Future. There's currently 14 of us, 14 research groups from University of Melbourne, Monash, RMIT. These 3 are in Melbourne, and we have University of Sydney and UNSW across in New South Wales. There's a lot of, it's a wild mix of people. So there are a lot of people who do, for example, spectroscopy, people who do theory, people who do experimental science. So is a wild bunch of us. We even have Selvi, who's starting to work in the area of machine learning, for example. So we cover quite a lot of grounds there. There's 3 focus areas. The one that I'm working in is solar. Then we also have, as I said, more theory and very detailed spectroscopy, where we try to understand how we can control exciton and their lifetime in different material. And we have a 3rd pillar where we are trying to apply everything that we learn about these excitons to make security features, for example, banknotes. So one of our partners is Banknotes Australia. The second center that I'm part of is the Australian Centre for Advanced Photovoltaics, or ACAP, as we call it short. It's the main node is here at UNSW, and it's led by somebody all of you here should know. It's Professor Martin Green, the Pope of solar cells, I usually call him. And there's also ANU. There's a strong group in ANU, Melbourne Uni. That's us here at Monash, and University of Queensland. Across the road from us, we have CSRO. That's our national lab, which is involved both in ACAP as well as the Exciton Science Center, and a couple of industrial partners as well. Okay, this is our lab in Monash University. It's a reasonably new building. Looks like something out of a Transformer movie, I always think. And we're based here on the 1st floor, have about 800 square meters in what we call our renewable energy lab, which are really, everything there is made for thin film solar cell research. We have the MCN. It's the so-called Melbourne Centre for Nanofabrication. I was getting a lab tour yesterday, and I think you guys are very spoiled. You have your photolithography, your electron microscopy, you have your etching tools, you have your e-beam evaporator, all of these nanofabrication tools that you have in the building. We also have access to it, but we just have to sit in the car for 5 minutes. and that takes us here to the Melbourne Center for Nanofabrication. We also have an electron microscopy center across 5 minutes walk from the lab. We have the synchrotron just outside where we are, and also the National Lab CSRO, and we work very closely with them. Cool. And that's a bunch of the people in the lab. There's about 30 of us, but that's just a few. And they're very proudly showing off our very first solar cell module that we put together. Other than myself, there's another 4 academics who are using this facility. There's Jack Jaziniak, Chris McNeil, Joanne Etheridge, who is mostly working on the electron microscopy side, and Sasha Simonov from chemistry. Okay. My group works on a couple of things. We work on single crystalline perovskite materials. I'll show quite a bit of that. Back contact solar cells, I'll also talk about that. Some examples of structure property relationship studies I'll show. Lead-free perovskites is something we're working on quite intensely at the moment, but it's tough. So I'm not showing too much data on that. Low-cost materials for commercialization is what the slide that we already saw on the carbon electrodes, the laminatable carbon electrodes that we have been working on. And I also would like to talk a little bit about not what we're doing now, but we would really love and what we will do in the future, and that's high throughput materials discovery. Somebody has to watch the clock, and if I'm taking too much time, you have to give me a wave and I'll skip the last couple of slides. Okay, I wasn't quite sure what the audience was. That's why I very briefly go back to what is a perovskite. So perovskite are generally materials that have an ABX3 structure. So we have a large cation A, so it's the yellow blobs here in that structure. And then we have a smaller metal cation, which in our case is mostly lead or tin, which sits in the middle of these octaeders there. And then we have the halide ions. This is very slow. Oh, doesn't matter. Which are coordinating our metal cation. So the halide ions, if we're making a solar cell, we're mostly interested in iodide, sometimes a bit of bromide, or chloride, which pushes the band gap open quite a bit. Okay. Again, for people who have not been following perovskite solar cells, just a bit of a comparison. We can make perovskite solar cells from solution processing. Silicon is quite an effort to make photovoltaic quality silicon. In fact, if you wanted to build a plant, you need something like $3 billion in terms of infrastructure to build that facility. Solution process perovskite solar cells you can pretty much do in your own garage if you set it up. Yeah, so it's very, very cheap. Band gaps 1.56 versus silicon 1.1. So they're both within a very good range where we can make high efficiency solar cells. The absorber thickness is typically about 1,000 times less than for silicon. Silicon is in the range of 300 micron, perovskite range of 300 nanometers. The efficiencies are very similar. Please don't beat me up if I have got those numbers slightly wrong, because they change every time. So we have efficiencies about 25.6 for the perovskite and just less than 1% more for the silicon. A nice thing is also that you don't always have to think, are we better than silicon? But you combine perovskite with silicon. And the last speaker we had comes one of the world's best groups that is working on that combination of silicon and perovskite to make tandem solar cells. And if you combine those two, you can get efficiencies up to 29%. The stability is what I typically call the Achilles heel of perovskite at the moment. So we have up to 10,000 hours, whereas silicon, you can easily go to a shop and find a manufacturer that gives you 20 years warranty for your material. Well, energy payback times, this is where we can beat silicon. And giving up, where is it? Giving up on this pointer. So we have 3 months roughly versus 3 years. That's the time it takes with a solar cell being on the roof until you get the energy back that it took to make it. Also very interesting, in 2020, there were about twice as many publications on perovskite than there are silicon. So even though nothing's on the roof on the science side, there's a huge interest. So twice as many papers. Okay. In a normal perovskite solar cells, we sandwich our perovskite absorber between a layer that extracts the positive carriers on top here, the p-type hole transport layer, and another layer that selectively extracts the electrons from that material. And that sits on a conducting glass slide. They're very, very easy to make. We're mixing two crystalline precursors, lead iodide, methylammonium iodide in an organic solvent, making a spin coating solution out of it, or and then solution process that and get a beautiful film like that. Now, if you take your spin coating solution and you just drop it on a glass plate and you let it dry, then you get something like this. Looks beautiful, but if you make a solar cell from that, the efficiency is somewhere maybe 1 or 2% or even less. So this is not it's a very beautiful way of making perovskite, but not a very efficient one. So what our group at Monash University used to do at the time, so we were one of the first to come up with the anti-solvent method. In fact, we had a patent on the anti-solvent method at the time. And also the next one that I'm showing you, which is going to be the gas-assisted technique. So what you have to do is, so you either with the anti-solvent method, what you're doing is while you're spinning your perovskite precursor, before it dries, you come in with a chlorobenzene. And yesterday we had a talk about that. And you need to get the timing right. Yesterday we learned that if you have a DMSO in your precursor solution, actually you don't have to be too strict on the timing. If you don't have DMSO, you need to be absolutely accurate. Otherwise you take big losses. And alternatively, what you can do is you can also have argon or nitrogen flow directed onto your perovskite and also create that fast drying and also get then these very beautiful films. We always see the nice crystalline images of our perovskite, but we also need to keep in mind that if the film is unannealed, this is what it usually looks like. Yeah, it's just amorphous. And the crystallization, then a lot of that crystallization in our case happens then during the 10-minute thermal annealing. Okay, I want to talk a little bit about back contact solar cells. So the work I did that I showed you before, that was in collaboration with Yibing Cheng and Leon Spitzer, my colleagues at the time. And now I want to move on to a field called back contact perovskite solar cells. And there we're working with our colleagues across at CSIRO, mostly Anthony Chessman. Back contact solar cells in a back contact, and I give you an image here of a silicon back contact solar cell. What you do, instead of having the contacts on top and below of your absorber material, you're hiding both of the contacts underneath of your solar cell. That frees up the space on top of the solar cell to optically couple the light into your solar cell. So that's one of the main benefits. So you avoid transmission losses of window materials, and you can also use an opaque substrate when we talk about thin film solar cells. Your conducting electrodes, there's no need for them to be transparent in any way or any optical requirements. They can be metals, for example, anything you want. And it's also easy to interconnect them once they come to sit on the same substrate. Okay, now if you think, how do I make an interdigitated electrode? The easiest, what you do is you have two sets of electrodes that like this. So this one here is collecting my electrons. This one here is collecting my holes, and they both sit underneath the perovskite. A disadvantage that we have compared to the silicon is that silicon has a charge carrier diffusion length of millimeters. In a perovskite, if we're very lucky, we have micrometers. So we need to make sure that whatever structure we create underneath our perovskite also has feature sizes in that kind of micron, even submicron, ideally, space. Okay, we changed that configuration a little bit, and what we did is now we have a non-patterned electrode on below. So this one is collecting the electrodes, and then we only have one set of fingers. So first of all, we put an insulator on, and then on top another finger which has the second electrode. So here we see, you can see this slightly greenish shaded layer underneath. That's an insulator, and on top of that comes the single finger now, which is the hole collecting electrode that sits on top of that. So we refer to that as quasi interdigitated. Oh, I need to go here. Sorry. Now you've seen it all. Sorry. Let's try this again. Somehow it's not coming up. I'm sorry. Yeah, what we have is now a back contact. We changed the design. I hope that yeah, it's here actually. So we changed the design again. And rather than having these fingers that are very sensitive, you need to think about the aspect ratio of them. So they're about a micron, in the order of a micron wide, but millimeters, thousands of microns long. So if there's a defect somewhere, you cut off the entire finger. So a structure that is much more defect tolerant is this so-called honeycomb structure, as we refer to. So imagine that you have a sandwich where you have your electron collecting electrode, insulator, hole collecting electrode, and now you're drilling holes into that material and exposing the electrode underneath. And that's pretty much what we have here. So you have, it's like having a grid of an insulator and then a grid of a metal collector on top here. So if you create charge carriers anywhere, they can either go to the top electrode or find the bottom electrode in their vicinity. Okay, in the interest of time, I might not speak too much to that slide here. So a conventional way of making them is through photolithography, and I'm not going to go into detail of how we do exactly do that. It's a very rock standard photolithography process. We usually always get trouble from our referees when we submit our back contact papers to journals. They say, oh, photolithography, we don't want that. It's expensive, it's complicated. Can't you do anything other than photolithography? So one thing that we tried is nano imprint lithography. So here we see that same honeycomb structure as a nano imprint structure. And recently we developed an alternative method, and that was done by one of my PhD students, CG Deng. And you can see here now, this is a 10 micron scale, and you see how this beautiful regular array of kind of a back contact honeycomb structure. Efficiencies also have gone up here. We're comparing the current voltage characteristic of a conventional back contact solar cell made with photolithography to one that is made with this mask-free lithography method that we just developed. And you can see it outperforms it quite nicely. So when we look at the right, it shows the stabilized power, our output. And there we're sitting somewhere in the range of about 8.6%. So generally with back contact, we're just making it above the 10% hurdle at the moment with what we're doing. I'm always threatening my group, say, if we don't have 10%, we're not going to make any back contact solar cells anymore. I've said that a few years ago. I should have closed the group down again, but I think we're slowly moving there. And there's quite a lot of theory papers that actually say that the back contact should be more efficient than the conventional sandwich. Yeah, it's just a bit harder because we have that length scale difference to silicon, where silicon has millimeters, we have only micrometers. Okay, so I want to move away a little bit from solar cells and talk about work that's been mostly driven by one of our postdocs, Wen Chin. Wen Chin is a research fellow from the Australian Centre for Advanced Photovoltaics. And the first project that I want to introduce here is done in collaboration with Xiaoliang Bao, who used to be at Monash at the time, and Trevor and Christopher Hall, who are colleagues of mine at Melbourne University and part of the same center that we have. Okay, now we're chemists and we want to do single crystals. When you're a chemist and you want to do single crystals, there's usually two ways of what you can do. You either heat up, you make a saturated solution, you heat it up, and then you let that almost saturated solution cool down slowly, and then you get your crystals. Another way that you can do is you can use diffusion. So you can have your precursors in here. Let's see whether this is working. No, cursor doesn't work for me. So you have a jar in here where you will have the precursors for your perovskite. Around it, you place that in a jar that has ether all around it. Now, if you put a lid on and you put it away, you don't look at it, and you come back after a while, you realize that the ether will slowly diffuse into your precursor solution. Your perovskite itself is very insoluble, becomes very insoluble in ether mixtures with other solvents. And what you generally get is you get the beautiful perovskite crystals come out. Now, Wen-Chin thought, oh, I'll do even better than everyone else, and I'm going to put this whole thing into the fridge. So he did it at around 0 to 4 degrees Celsius. And surprisingly, we didn't get the orange crystals that we expected, the methylammonium lead bromide in this particular case, but we got some white material. And this slide here shows you again. So we got this stuff. Any ideas from the audience of why we got this and what it is? No? Yeah, we also were puzzled for a bit. So that's a millimeter scale. We get several millimeter long needles. So this is the one we had. So we actually had a one-dimensional kind of perovskite-like structure. And that was that methylammonium lead bromide with the DMF solvent integrated into it. And this is an animation that shows a little bit. So you have these double columns of your perovskite octaeders, PBI6 octaeders that form these 1D structures. Now, the nice thing is if you take them and you put them on a surface, a droplet, and you let it warm up to room temperature, the perovskite is going to form. And now, because we had to shift my talk from my laptop to another computer, the next video is most likely not working, but that's why I have my backup here. So here you can see that at the very beginning, you have mostly your 1D material. And as it warms up, you can see how the needles start to melt and to go away. And then your plates, your perovskite platelets start growing. Oh, wow. I would have never thought that. So we have the video. Cool. So yeah, just because it's so nice, we're going to upside do that again. Okay. Yeah, so this is how we can make very high quality platelets, perovskite platelets. And cool. One more thing that Wen-Chin developed was he realized that if he pre-treats the surface onto which he drops that precursor solution, it makes a huge difference. And the reason simply here is that just geometric limitation of your film thickness. So your film becomes much, much thinner if you plasma clean your surface and the contact angle is very, very small. And that means that if we have a big droplet, we get almost cube-like structures. If we have the very, very thin film, we get these beautiful platelets. Shown this here. So these all look all quite similar in terms of their height. And here, if we don't do that, we get all sorts of things in our structure. One thing we did, we used focused ion beam milling. So we took one of these platelets and then cut a ring out of it. So this ring comes out of a single crystal. And what happens is if you excite the center here, this part here, what you can see is actually there's some wave guiding going on, and you can see whatever fluorescence you create inside your material. It's going wave guiding and reaching the ends of your circular structure. And that too. So we had a similar structure here. So they see this one here. Now imagine that you take this perovskite and you place it onto a silicon wafer that has a thin silicon oxide layer on top. And then you evaporate silicon oxide on the two sides and put again a gold electrode on top. Now you have your perovskite sandwiched between two insulators and two electrodes, and that allows you to apply an electric field to your perovskite. So that's shown here. So you have your silicon wafer, which is quite strongly doped, so it is conducting, so we can use it as a conductive substrate, a layer of silicon oxide on top. And so that's our bottom structure here. And then we put again silicon oxide on top and a gold bridge across. So here's the spot where our perovskite is sandwiched between two electrodes, but we we can't have charge injection into the perovskite because there's silicon oxide between or on both sides. So it's really just an electric field that we can apply there. Okay, and then we saw that now what we're doing is we sit at the end of that wire, and we look at how much light is coming out at the end of the wire. And we look at that as a function of the electric field that we apply across the perovskite. And there we can see that we can almost completely shut off any fluorescence simply by applying a field. So what we have built here is an electro-optical modulator with a perovskite material. Cool. So there's one application. We also use those crystals to look at photo-induced phase segregation. Perovskite, one of the amazing properties of perovskite is that you can tune the band gap, and the most effective way of tuning the band gap is by changing the halide ratio. So if you have a pure iodide perovskite, it has a band gap of somewhere in the range of about 1.5. If you have a pure bromide one, it has a band gap in the range of about 2.2. And any mixtures of bromide and iodide in between gives you band gaps that sit between those two extremes. It's fantastic if you think about it. The problem is that, and that's also very important for making tandem solar cells, because for a tandem solar cell, typically 1.5 is not ideal. You would much rather want something that is in the range of about 1.7. So that's where this halide tunability is very, very useful. Now, the problem is if you shine light onto, for example, a bromide-rich perovskite, so that we start off with a red line here. And as we shine light on it, we see this fluorescence peak of our bromide-rich material disappear. And instead, we actually see the luminescence of the iodide, of an iodide-rich phase. So what happens is that we create these small centers that are very, very rich in iodide. And we don't have a homogeneous material anymore. So we have a material that has bromide-rich domains and has iodide-rich domains. And because it's not homogeneous, also the electrical properties and optical properties are not what we want from it. So that usually is a bit of a problem. And previously, people have always thought that this is due to the grain boundaries. And iodine-rich phases were observed to form near those grain boundaries in polycrystalline films. And there was a general theory around grain boundaries being at the center of that phenomenon. So we studied the same thing with our crystallites. The only thing we had to do is make our same precursor, but not make it with a pure bromide, but a mixture of bromide and iodide. And make these mixed halide platelets. And here's an example of that with EDS mapping to show it's homogeneous. And let's see whether we get lucky a second time. So what we do now is we take one of these platelets and we shine light on it. And we have a fluorescence microscope camera that is only sensitive to the iodide-rich fluorescence. So if we don't form the iodide-rich phases, we're not going to see anything. You see here at the very beginning, this is what we start off with. So let's see whether that video is playing. Oh, okay. Lucky day. So this is in real time. And I think this is a lot of what we see at the boundaries here is waveguiding. So don't look too much at the boundaries, look at the center. And here you can see how these domains are shining up, which are rich in iodide. So here we could show that, unfortunately, that halide demixing that everybody always thought is somehow linked to grain boundaries actually also just as well happens in a single crystal of perovskite. Okay, and here we're plotting the fluorescence. So red means strong, blue means weak, in false colors over time. So here we see this is our bromide-rich phase that we start off with, or the mixed phase. Has a fluorescence here, and then as the iodine-rich phases are forming, you can see that their fluorescence come up here at around 750 nanometers. Yeah, and that happens within 50 seconds, 100 seconds illumination. That phase segregation phenomenon comes up. Yeah. And we can do that. We can let the crystal recover again in the dark, and we do it again and again, and it happens over and over. And something that was interesting for us to see is also that once you form a halide-rich domain somewhere, you let it relax in the dark, it goes completely back to fully mixed. And then you do the halide segregation again by shining light on it. You look at this one here, it appears in all the images, yeah, in the first cycle, second cycle, third cycle. And then there's others that were kind of weak before or not there at all. And then they get stronger and stronger as you go from first cycle, second cycle to third cycle. Okay. Might also skip that. How am I doing for time? I'm fine. How much left? Don't be too generous. People have been sitting for a long time already. 10 minutes. Okay. Good. Then I might just jump here. So here, that's a similar image that I would to what I just showed you. We're starting off with a green fluorescence. Green is from the fully mixed phase. And then we shine light on it, 10 watts per square centimeter for about a minute. And we end up in a fully phase segregated material. That's what everybody would expect. Now, what will happen if we shine light on that is, say, 100 or even more times more intense? What would be your guess? My guess would have been more of the same, yeah? But what's quite amazing is that if we now switch the light source and we shine high intensity light onto our crystal, what we see is actually it's reverted, yeah? Now, if we shine 200 watts per square meter light onto the same crystal, onto the same spot, our phase segregation, our halide demixing goes away and everything just mixes nicely again. So the same thing that caused halide segregation can also make it go back to fully mixed. So that's something that was quite intriguing and then we found quite interesting. And here's an image of a crystal. So one of these platelets. We have a low energy, or 10 watts per square centimeter background illumination. And here in the center is where we're illuminating with a high intensity light. And you can see that here in the center is where we cause the remixing. And in the boundaries, you still have your segregated state. So that can,
depends on the intensity of the light.
Correct. Yeah. And we're also working with our colleagues at the University of Sydney, and there's a theory group, and they have come up with a polaron model. And so if you think of yourself as a charge carrier, a hole and an electron in an already phase segregated perovskite, the band gap in the iodide-rich phase is much smaller than in the bromide-rich. So you as a charge carrier, you can gain energy by going into those areas where you have your halide, your strong iodide concentration. So you'll be trapped in these areas. So that's where you want to be. If you're a charge carrier, you want to be in these areas. Now it turns out that if you think also about if you think of a halide, those charge carriers also come with a lattice distortion. In an area where there's lots and lots of charge carriers, if you're an iodide in this mixed halide perovskite, you're slightly bigger than everyone else and you feel somewhat uncomfortable. You're causing lattice strain, and the iodide ions can minimize their lattice strain by moving across from a general area into one where you have these iodide-rich phases, because that's where the strain is less. So you reduce the strain of the carrier for the iodide mode. So you have a driving force for the iodide ions to move into areas where there's lots of carriers. And you also have a driving force for carriers to move into that area where you have lots of iodide. And that is kind of a self-reinforcing mechanism that once you form these kind of halide segregations, this is where it keeps. But then if you start having more and more carriers in your material, the gradients here, so here you have a lot of gradients. So if you think about being an iodide ion that can move in the perovskite, moving from here to here gives you a lot of gains. But once you have an enormous, you have the high intensity light, then as an exciton, the whole perovskite will more or less look the same. So you don't have that driving force anymore for segregation. So that's a model developed by our colleagues at the University of Sydney. And I think now we also recently did some work on looking at those twinning domains in perovskite, but I think I might just jump across that. And that's also done in collaboration with people at Oxford. And Matthias, have you met Matthias? Yeah, cool. Some just jumping on. So in a nutshell, what we saw was that if you look at methylammonium versus mixed methylammonium formamidinium and pure formamidinium perovskite, this one has a lot of these twinning domains. So it's more like a mirror axis in your crystal. And when you go to MA 0.8, FA 0.2, that's somehow the golden range. This is where we see absolutely no twinning. And then as we move on again to the pure formamidinium, that the twinning comes back. And in a nutshell, what we could see is that there's a correlation between the twinning and the performance. So when at this magic combination here at 0.2, we don't observe any twinning, and that's where this is our hysteresis index. You see the hysteresis index is the lowest in this area, and also the efficiency of our forward and backward kind of has a maximum here. So we think that there is a correlation between those twinning planes, the defect being the twinning plane, and the performance of our solar cell. Twinning planes, there's also a theory that the twinning planes allow for ionic conductivity. That's where you have enhanced ionic conductivity. And that's also why the hysteresis index here is quite high and is quite low, where you do not have the twinning domains, because you cut down these ion migrations. Okay, now let's talk a little bit about not what we do, but what we want to do, and what I spent a lot of my time over the last couple of years to do. So we talk about material. What we want to do in the future is high throughput materials discovery. Comes to sit somewhere between material science and robotics and artificial intelligence. And this is what we have ordered. So it's currently in the process of being put together in a factory somewhere in Switzerland very soon. So we ordered that sometime last year. It's a 10-meter long glove box system. It has a unit here that can do chemical synthesis. So you have your powders, your solvents, you have a balance, and you can dispense things, mix things, steer things. Then those spin coating solutions, the solutions you make, are moving on to the next box. That's where you have a automated spin coater that also can do anti-solvent technique or gas-assisted techniques, which sits here, and also has 10 small annealing plates around it, where you can thermally anneal all of your samples. So this is where you make perovskite, or ideally, hopefully in the future, not lead perovskite, but kind of a replacement for the lead perovskite. I think the lead perovskite is so advanced, maybe we don't want to work in this area. So we want to really move to kind of discover new absorbers that have similar properties to the lead perovskite, but don't have the toxicity, the stability problem, etc. And then we have another glove box here. We have a couple of characterization tools sitting in that one. So we go from powders and solvents to thin films, and then characterizing these thin films. We also have a theory that, at least in a first iteration, we're not necessarily interested in making a solar cell device as such. Because if you think about having an entirely new material, you don't know what materials to use to contact with it. What's a good electron extraction layer? What's a good hole extraction layer? How do you control those interfaces between those two so that you don't mess that up? So we're hoping that we can use basic physical characterization techniques to just make a film, and without necessarily contacting the film, putting kind of electrical contacts at the top and bottom, we want to understand, is it a good material or is it not? And So I kind of spoke to that already. So we have our different dispensing techniques for the powders and for the liquids, on-deck balance, shakers, and so on. The spin coater, the annealing stations. And then in terms of characterization, we already have an electrochemical characterization tool. And I kind of sneaked that one in. Don't tell our funding buddy. I sneaked that one in because I thought, well, if we have this, if we have an electrochemical tool in here, think about you wanting to do research on a new solar fuel catalyst. You can do it. Here's you can do a cyclovoltammogram with this electrochemical characterization tool with every film that you produce in your robot. And you can check, is it a good catalyst for doing the conversion for whatever I want to do, water splitting, nitrogen fixation, whatever it is. And then more on the solar side, we have the UVVs and absorption spectroscopy, and we have steady state fluorescence, and hopefully if we can afford Raman. That's still the last thing where I haven't pressed the button yet on because I'm not quite sure about the budget. And we have an optical camera. This is what I feel is the core, the heart of the whole thing, and that's TRPL, so we may do fluorescence lifetime, but also time-resolved microwave photoconductivity. And so what you do is you put your sample into a microwave waveguide, and you're measuring its capability to absorb microwaves, time-resolved. If you create a charge carrier, and it's usually the electrical charge carriers that are strongly absorbing those microwaves, the absorption is stronger the more mobile they are. So you kind of already get a sense for the mobility of your carriers, and you get a sense for the lifetime. And hopefully you can also calculate something like the diffusion length of your materials. So if you're a solar cell researcher and you're looking for a new solar cell material, that is quite valuable to have all this information there. So if you get a very strong response there, nice lifetime, strong signal, meaning high mobility, then you know, okay, now I just made something that is worth exploring further. And then you can start scratching your head about what materials to choose to contact it and to make a good solar cell. And then also XRD, so we can get an XRD and a profilometry. The idea is that we do, everything moves on in 5-minute clock speed. So every 5 minutes you get a new device made and fully characterized. And the idea is also that we can press the button and have it run for 24 hours, hands off. Let's see. Yeah. Okay. So here again, we have automated chemical synthesis, thin film formation, film characterization. Then I think we need some automated data analysis kind of on the fly. So when we look at TRPL, we don't want to feed the entire TRPL into something, but we want to just extract, for example, what are your lifetimes? What's the lifetime? And already extract that lifetime and not just the entire TRPL trace. And then we need to have a data archive, high quality data archive. This I think is very important. I'll come back to that, some machine learning that helps us to cope with all that data. And then we move back into the loop. Can be applied for solution process solar cells, heterogeneous catalysis, supercapacitors, luminescent solar converters, and photon up conversion. This is one of my favorite slides, and my students are already smiling when they see that because I show it over and over again. It's some work from Henry Snaith's group. And what they do is they have this, it's maybe a bit small to see, but they have this lead acetate and reacting with 3-methylammonium to form the perovskite. And this methylammonium acetate, which will evaporate off, so as methylamine and acetic acid. And what Henry and his group and in the collaborators showed here is that, let's move on the power conversion efficiency. You see here is factor, I said it, stoichiometric is 3:1. So here's your 3:1. And now you're slightly changing. So this is actually 3.03. So it's 1% off. So you change your ratio by 1% and you moved from a solar cell that has like less than 14 to something that has something like above 15%. Simply by changing your ratio by 1%. And this is also something where we think that if you have a system that very, very accurately at least monitors what your ratio is, it'll be much easier for you to do your optimization of your solar cells. Okay. Right. So maybe just look at these two pictures and they show what we fear for the future. I recently was in a group meeting and we spent an hour discussing about 2 XRD spectra. And I thought, oh, if we have this thing, we're going to have 2,000 XRD spectra every week. What's my life going to be like? So I think what we need is we need to change the way we look at data and deal with data. So I think we need some help with machine learning. So this is, I estimate about 20,000 spectra a week if everything works well. And I don't think we can physically, with our brains, just manage that. We need some help with that. So we need machine learning, data processing, data visualization, automation, and we need to collaborate on that. And here comes the most important slide of my presentation. We're looking for brave PhD students who are happy to join my group and play with the robotic system. Yeah, so some people in my group say, oh, you're buying this robot so you don't need PhD students anymore. They're completely wrong. Once we have that, we need a whole army of PhD students to actually run it and then manage the data and chew through that enormous amount of data that we're generating. So that's me. I tried to acknowledge my co-workers already as much as I could during the talk. Last but not least, obviously, need to thank my team, and above all, obviously, Sonia here, who made it possible for me to be here today. Very sad to see her go, but I was very happy too, because I saw she's going to an amazing opportunity here. All right. That's me. Questions? Thank you.
Thank you very much. Very interesting work. I have a lot of questions. I have some questions. Let me see if we have some questions from the audience. We have one here, I think. There used to be, this is Gustavo Catalan from our institute, there used to be a controversy about whether MAPI is ferroelectric. What that question has been resolved, do you know?
Yeah, there's a huge discussion on that. And I think the question must have come up because there's a link between ferroelectricity and twinning. I think all ferro, and I don't know the answer. So typically materials that are ferroelectric also have show the twinning. I don't think we have the final verdict on whether or not the MAPI is ferroelectric or not, and I don't want to be the judge of that because we're just not in that area at the moment. But I know there's a huge controversy of, there's people who do experiments. They say, look at my experiments, it clearly shows that it's ferroelectric, and there's other groups that contradict that. The fact that we have twins is kind of pushing towards the fact that it should be ferroelectric. Yes. Yeah.
Hard to measure because of the properties of the,
Yeah, I think one thing that's definitely in your way is the ion mobility. As soon as you apply strong electric fields to your perovskite, just your ions are just going to move all over the place, and then that obviously gives you then a polarization signal when you do that.
the problem is when you send conductor and then you don't have electricity, so there's a game that is very challenging there.
It's very challenging.
Okay, and any questions from the audience here?
I have one question. Just one last question. I want to see if I understood correct your expression about the polarons and that intensity relation to the intensity light exposure. Is that correct that you said that in low intensity we have polarons formation? So because of the segregation of the iodine and bromide in different areas, but in higher intensity, then the polarons dissociate actually because of
no, they don't know what a polaron is a charge carrier plus the strain that it causes around it. And at high intensities, you still have your carriers, and each of the carriers still has their strains. But if you think about at low light intensity, if you're and the polaron there, so I need to be careful what I'm saying.
Because when you have too much, I mean, and a lot of carriers, they dissociate themselves from the strain. So they can move around, as you said. So this will be like, you know, that the polarons doesn't have the more definition.
Yeah, it's more a question of how many there are. So you still have your polarons, but because there's such a high intensity that you don't have your gradients anymore in terms of there's a polaron here and there's none there, because they're just all over your material. So you can't pretty much saturating your material with polarons. So you can't have that kind of polaron free areas in one area and not others.
Thank you.
Yes.
The single crystals you showed of the MAPB bromide, do you know the dimensions of them, like how thick they are and roughly?
We can make them sub-micron, and they typically are tens of microns. I think I had the scale bar on some of them, but typically tens of microns, and typically we can tune them so that they are sub-micrometer.
How do you know then when you have like the camera that was like on one of like the iodide X, that it is not coming from the grain boundary when like from the top surface, maybe if it's like still like a bulk phenomenon of that?
Okay, you still have your, but you have that. The surface, you can still have your top surface defects, and this could have an effect, but it's definitely not the grain boundaries inside your material. So what happens on the surface, but even if it's a single crystal, I would also hope that the surface of the single crystal is quite perfect. But then when you come in and you say, well, maybe you had defects on your single crystal, maybe even one of our referees was querying that. I wouldn't rule it out that there could be a possibility that it was whatever defect or yeah, defect is the best word, defect on the surface, and that's where it also, because it's a self-stabilizing thing, and it has to start somehow, somewhere, for some reason. So if you have some imperfection somewhere, it could be the starting point for that. Yeah. Yeah.
Thank you. Do I have to press somewhere? Okay. I had a question about the timescales for the recovery of the phase segregation.
Yeah.
So when you saturate it with the high intensity light, is that faster than if you just leave it in the dark with the recovery?
Oh,
Yeah, because I mean, I guess it's a diffusion kind of regulated process. So do you know more or less the difference in the time?
And from what I showed there, I think within a few seconds we have it. I don't know the exact time scale for the dark remixing. I would say it's maybe at least a factor. I would say it takes minutes for it to go away completely.
The saturated light state to the dark, does it stay stable there, or do you see any other changes?
Say that again.
So when you had the switch that off to a dark state, does it stay stable there, or do you see further changes due to that high?
I don't think we did that, because it's already mixed, and then the question is, does it stay mixed, or does it go mixed, unmixed, and then back to mixed? I don't think we even did. No, and you can go through it a couple of times. That was also one of the referee questions. So can you run through several cycles with the same crystal? And yes.
So about this phase segregation that you saw at low light intensity, that's
Low.
low.
It's still 10 watts per square centimeter, which is.
But how can we relate that to the applications of this Halide Perovskite for indoor lighting?
Oh, indoor
That's
lighting. Low. We have to be a bit careful what we call low and high, because low is already very high. So if you think of AM 1.5 is 0.1 watts per square centimeter. What I call here low is 10. So we're already quite high above. But if you further push it, so you really have to push it a lot to say beyond the, let me think again. So we start 10 watts per centimeter. That's already a factor of 100 away from sun. So you have to go to 1,000 suns to have the remixing. So if you think, for example, of a solar concentrator, can I have a solar concentrator where the light intensity is high enough so that whatever phase segregation phenomenon I have can be reversed? But then you would have to go to these very high intensity. But I think it's my mistake for calling it low and high, but because you were thinking indoor is much less than what I was showing here. Yeah.
About the scale.
Yeah, that was my mistake for calling low, but it's actually already quite high.
So those of us that work on the use of additives for this Halide Perovskite in solution processing, what we are trying to do is to see this. If we see this ion movement, we are trying to trap them and stop this movement. Okay, so immobilize them with additives. But what you saw in your crystals is that, of course, you have movement inside, but you are not going to be to put additives inside this crystal to make it immobile. That's a problem.
Yeah, I think, in general, I think the halide mobility is a problem, and you have additives, as you say, that can kind of stop that mobility, or the other way is, my understanding is not necessarily the halides that are mobile, but strictly speaking, it's the lack of one, the vacancy. So you actually have, once you have a vacancy, something can hop in, and that hopping process of a halide from where it is into the vacancy, that is de facto the displacement. And so you actually have the vacancies moving around. Now, if you can make a material that is entirely free of vacancies, you should also not have phenomena such as phase segregation, because then your ions can't move anymore.
So you're telling me that in your crystals you probably have some vacancies there. That's why you observe that movement. That,
or you need to come up. You need to think about a mechanism where, for example, the interference with light causes your halides to jump from where they are into interstitial. And then, so if you have if in equilibrium with at room temperature or whatever the temperature is, your halides jump out of their spots and become interstitial, and then you have your vacancies, and they can move, and possibly that can be enhanced with light, which I don't know. That's another mechanism that I can think of, but I have no idea which of the two is realistic.